Uh, Thank you for the wonderful intro, and thank you to the lovely East Belgrade organizers for organizing this event. They're great. And yeah, hi, hello, my name is Vukasin. You might know me as Make. I work at Enso. Uh, I do a bunch of open source work. And yeah, we're going to be talking about async Rust. So this is going to be a mid-level talk going over asynchronous programming and various multitasking modes. I've tried to make it pretty accessible, so if you have some programming knowledge, you should be able to follow it. We'll cover various topics like various multitasking models, asynchronicity, brief history of async Rust to get more context about how and why we got here, how async Rust works, and how it should be / shouldn't be used. So I'd like to get like a show of hands. How many of you people here work with async Rust? Right. Yeah, here and there. Okay. Nice. Oh yeah. Also, this is as a slight bonus. It's not Rust specific, but it's very Rust focused. We cover lots of topics. So, yeah. Let's talk multitasking. So, in the olden days of computing, we had computers with only a single core, and they couldn't really multitask. They could only do one thing at the same time. And now, we have phones with 12 cores and thousands of background processes running in parallel. So like, to understand how we got here, we need to go a bit deeper. We need to look at the OS level to figure out how things work in parallel, even when programs are single-threaded or when they misbehave and become unresponsive. So let's talk about preemption. So think of preemptive multitasking like a busy chef in a restaurant kitchen. So the chef has to manage multiple dishes at the same time, and instead of spending all of his time on a single dish until it's done, he splits his attention between multiple dishes so they're all cooked properly. So preemptive multitasking is a paradigm where tasks run at the mercy of the operating system scheduler. Schedule is basically a part of the kernel that decides for how long something should run, how much CPU time it should get, and in theory, everything should get equal CPU time if they have equal priority, but too much information probably. So the CPU will be running some task, and you will get like a hardware interrupt. And what basically happens then is then the CPU will run the interrupt handler. And the interrupt handler will go and say, okay, let's ask the scheduler what should be run next. And generally on modern systems, the interrupt is a time-based interrupt, whilst on like older computers are like keyboard-based and mouse-based. That's why like PS2 like ports, for example, they interrupt your CPU. We don't really do that anymore. But yeah, as we can see on the graphic, those like these pens work well. Doesn't matter. So we have like task K1 when like program A executing on the CPU, and we have like some hardware interrupt that forces the CPU to run the interrupt handler, and the interrupt handler will run the scheduler, and the scheduler will go, okay, task K1 ran for long enough, let's give task B1 a chance, and then task B1 will run. Great. So because we're interrupting tasks without being aware of their state, we might interrupt them while in the middle of doing something. So in order to resume it later, we need to be able to back up their entire state, so call stack registers, anything. And this is called a context switch. So as you can imagine, backing up everything is pretty expensive. So what we do is we make a new call stack for each process. A task with its own call stack is called a thread. So with this approach, we just need to back up the registers, which maximizes context switch performance, which is pretty important considering we're going to be doing this thousands of times per second on a CPU core on a modern, for example, phone or a laptop or whatever. So preemption is good because it lets the scheduler control when tasks run. In theory, each process should get an equal amount of CPU time. Another benefit is that tasks don't need to cooperate, so a task can become unresponsive and it can just kind of like, it won't freeze the system basically. Other things will also run. So, but unfortunately for performance reasons, we need to like keep extra data in memory, which kind of sucks, but it's a cost we're willing to take for all the benefits above. Yeah, software sucks, too bad. So what if we all like held hands and like decided to agree and like, you know, well, we don't, we have cooperative multitasking. It works by letting the program decide when it's ready to context switch. So this is useful if you're waiting for something like I/O, for example. Ooh, foreshadowing. Anyways, in cooperative systems, programs will yield once they're ready to context switch, and they will only back up what they need to back up in order to resume later. So yeah, this is very useful if you are working with systems with limited constraints, like if you're working with embedded stuff or things like that. So let's look at the following code example. So on a modern system, these two threads would be executed concurrently. But in a cooperative system, work gets done until yielding. So this will be pretty much sequential if it's CPU bound. In a case like this, if a thread does not yield, it will take all the CPU time for itself. So yeah, we have like this child thread, and we're like doing like an infinite loop in it. And because we're not yielding, we're just running this, and our very important work down here doesn't get done because this like blocks it. So also a fun cooperative multitasking fact, the Nintendo 3DS operating system Horizon, which later gets used on the Nintendo Switch, is entirely cooperative multitasking. So it uses a thread with a priority. So basically like how it works is threads get spawned with priorities, and if you have like threads with the same priorities and one of them blocks, like your whole system will get blocked. So that's fun. Cool, but like how did we get here? So what I mean by this is, why does Rust async look the way it does today? So the question is important because it gives us context about how it works today and the mistakes that led into its development. So fun fact, throwback to pre-Rust 1.0, Rust used to have green threads built in, but it was removed for the reasons we're going to discuss in a bit. So if we go back to like multitasking, we're going to like remember like the huge RAM requirements. Well, to mitigate this, green threads deal with this complexity in two ways. They either like have segmented stacks, which work really well, but have inconsistent performance. So what I mean by this is if you allocate memory and like everything fits, then great. Like it's basically a linked list. So if you add to the linked list and you have enough memory and you don't need to allocate more, then great. It's free basically. But if you have to allocate memory, then it's like a huge cost. And then like stack copying, which also works, but stack pointers become invalid because you have to copy the stack on every allocation. It works similarly to a vec, or like vector in Rust, so yeah. Go use the stack copying, but it only allows stack pointers within the same stack, and this won't work in Rust because Rust does not have a runtime, and Rust just does not have enough context about the types to like deal with this. So we kind of like run into this problem again later when we implement futures, but we'll get to it, and it gets like solved in like a pretty elegant way. So a brief Go hating interlude. Who here worked with CGO and FFI with Go? How bad is it?
0 out of 10.
Yeah, it's awful. Yeah, it's really bad. I'm mentioning this because you will have to do FFI or foreign function interference with like C code eventually. So one of the reasons why CGO is so bad, for those that don't know, CGO is the way you do FFI with like C or Rust with Go, is because of green threads. So in order to like do like FFI with Go, you have to go from Go green threads to system threads. This is a huge cost, and it's very, very, very painful. So Go kind of just like raw dogs it. It just kind of takes it like a champ. Well, we kind of don't want to do this for Rust because it goes against our zero cost abstraction principles. So Rust essentially, pre 1.0, with its like green thread systems, wanted to have two APIs, one for like green threads and one for like without them. And it's like, okay, that doesn't really work. So yeah, we kind of got rid of them. So it was very clear that like green threads need to get the fuck out and that are not good enough for Rust. So initially, Rust copied the continuation passing style, also known as like promises and like things like JavaScript. So yeah, this is like how you would like define this. Yeah, you have like a continuation after like the task is done and like that's get executed. So yeah, but this kind of sucked because it like didn't really work. It wasn't zero cost abstraction-y. It required you to like constantly allocate memory, and it was just bad vibes. So to understand, I have this like code example. So this function takes two futures, F and G, and returns a new future that yields a pair when the results from both get like done. So the joint future completes only when both of the underlying futures complete, but allows the underlying futures to execute concurrently until then. So how we will implement join using the above definition of futures? Well, we will have to have a single callback which expects a pair, but the underlying futures each one their own. So what we would do is we would have to have shared state between these futures, and we need to wrap this in an arc, and it just gets really messy, and we're constantly allocating to the stack, and not the stack, to the heap, and yeah, it's a bit of a mess. So in C, to handle this, programmers would handle async by building state machines. So what if we just apply this concept to Rust? So on the right here, I have what the state machine looks like in C. Remember this, it will become very relevant later, especially this struct. Yeah, it might look something very similar to what we have now in Rust. But yeah, so, oh, this slide is out of order, I think. Or is it? Oh no, it isn't, cool. So, okay, yeah, anyways, iterators. So, no, wait, what the fuck? Well, this is wrong. Anyways, yeah, well, iterators, wait, no, whatever, okay, I'll have to improvise. Anyways, Rust futures look very similar to iterators. So, iterators behave in a very similar way to Rust futures. So iterators are just state machines for iteration. So yeah, if you see here, we have a trait iterator, we have some type item, and we basically poll the iterator kinda, and if there is something to be expected, we get it, and if not, then yeah, no. So yeah, we have futures. So we have a low-level future state, and using user-facing combinators like map and then, etc. But there was a problem where you couldn't borrow across awaits. So there were some macros early on that kind of copied the async await syntax we had, but they were bad. Well, they're not necessarily bad, but they behaved differently to what we have now, because you couldn't borrow across async points. So you had to wrap things in arcs or use shared state or yeah, it wasn't ideal. And if you didn't use those macros, you would have to write root Goldberg code like this. Look at this, it's disgusting. So yeah, what the fuck? Nobody wants this. So yeah, let's try again. It was not possible for a future to hold a reference to its own state across awaiting. So, and to have this, you would have to have self-referential structs, which Rust cannot really do in a safe way. So it's interesting to compare this to the problem we had with the green threads again. So one way we've explained the compilation of futures to state machine is to say that the state machine is a perfectly sized stack. We already know what we need to hold while we're yielding. So but the stack is like a struct, and structs in Rust can always be moved, but we don't necessarily need to move a future, but we should be able to. So we have the same problem of the stack pointer problem. So this time we just need to say we can't move it. We never actually need to be able to move it, if that makes sense. So state machines need to store local variables in a struct at each point. So yeah, my slides are out of order, so this is kinda, let me yeah, okay, I guess some slides are missing. That's unfortunate. Yeah, this should be yeah, whatever. Anyways, yeah, as we said previously, the state machine transformation, yeah, well, did I explain state machines? How async does state machines in Rust? Okay, well, basically a slide is missing. So when you do async in Rust, it transforms your Rust function into something like this. is there like a future example? Is there like a future state somewhere here? Okay, yeah, cool. So, awesome. This is all out of order. So basically, no, this is like, okay, cool. So this should be like before. Yeah, when you do async, you like get something like this. This is like the future state. And you return impl that, and you struct is like this. Yeah, this is rough. Anyways, yeah, state machines need to store local variables in a struct at each pose point. So let's consider the following function. We have like some async function foo. We have an array inside of it, and we have an element that's a reference to the array. And then we like do some async writing to the file, and then we like dereference it and return it. Cool. So what we need to do is we need to store the array and the element of the array. So why do we do this? Well, we have an element which is a reference to an element of the array. So we have like this address of the array that's like this. And this is called a self-referential struct. This is generally a pretty big no-no in Rust. So this works really well until that array needs to be moved. So here we see that like before moving it, yay, it works great. Oh, it works great. We're pointing at the right element. But as soon as we like move it, we have the problem of like this pointing at invalid memory. So we have three options basically. We can update the pointer and move. We can store an offset instead of self-references, which is kind of bad because then the Rust compiler would need to like detect every self-reference, which isn't realistic when we allow self-references, or we can just forbid moving of the struct. So what we do is pin. So pin is like the cheapest and most elegant solution we have to this. Basically what pin does is it says, okay, keep this keep this area of memory as is. So just like keep this at like 0x104 and like don't move it at all. Just keep it there. And this was designed. Pin was designed in a way where you aren't really going to be interacting with it as the user. And as a side note, the entirety of async Rust was designed like this. Chances are, if you've worked with async, you didn't really have a chance. You're not going to have a chance to like implement features by hand. It's really nice in that fact. It's very user friendly. But yeah, back to the slide. Yeah, we got features that behave like state machines. Instead of storing continuations, features are polled with executors, which we'll talk about in a bit. And when a feature is in panic state, it stores a way to wake the executor, which is important. And once ready, it will be executed. Great, success. So what does async Rust do? When you make a function async, it gets compiled into a state machine. It lets us pull and yield and do cooperating multitasking in a kind of zero-cost abstraction way. So async Rust can run on pretty much anything as long as you have an executor. Executors are like things like, they're basically runtime. So for example, Tokyo, Small, Polster, these are executors, and they pull futures. This design is less different from this. This was exported wrong. Too bad. Yeah, basically, this makes async Rust harder in some areas, well, way easier in others. So, for example, because you still have like all the Rust borrow checker and memory guarantees, you don't really have to worry about data races and such. So, when should you use async Rust? Are you waiting a lot for something to complete? Async Rust is for you. Async is perfect for I/O. So this means like disk, networking, whatever. It allows much cheaper context switches than OS threads because it's cooperative. When we are ready to yield, we're going to store what we need to yield and then like do other things. So, and to clarify what I mean by waiting, we're not waiting for compute here. We're not saying, okay, I'm waiting for some computation to get complete. You're CPU bound. We're waiting specifically for I/O, so when we're I/O bound. And which is a great segue into when you should not use async Rust. So I'd like to present a problem. So how many people here know about function coloring? Nice, cool. So yeah, the problem goes like this. So every function needs to have a color. So we have blue functions and we have red functions. Um, Functions are called differently depending on their color. So you can call a blue function from within a red one, but you can't go the other way around. And the obvious choice is to just use red functions, right? Well, in our hypothetical, red functions are harder to call and use. And this draws a clear parallel between the three languages we actually have within Rust. We have async Rust, we have unsafe Rust, and we have regular safe Rust. So basically, yeah, you should avoid using async and unsafe unless you really need to. You should treat these two as kind of mini unsafes. They modify the way your code is going to be called and used, and if in general you're going to be writing regular safe Rust, so yeah, try to avoid these two unless you really need them to. If you want to read more about the function coloring problem, you can scan this QR code. That's a great article from which I nicked these examples from. It raises some very interesting points. And yeah, so if you're not IO bound, do not use async. Async adds complexity. It adds unnecessary transformations to the code, and consider the fact when writing async functions, everything surrounding them needs to be made to work with async. So if you're not writing async code and you need to like use an async function, you need to use something like block on, which is not ideal because you're going to be using code that was not designed for your use case. So yeah, if you're CPU bound, there will be many places where async functions can even context switch. So to conclude, async Rust is really good if used properly and painful to deal with if not. So the async hero transforms the async functions you write into state machines that can get compiled to futures. Rust does not have a runtime, instead it relies on executors. So for example, as I said previously, Tokyo, small, poster, all these things. Rust async is really good for IO-bound tasks, but counterproductive for CPU-bound use cases. And yeah, you should probably avoid async Rust if you don't explicitly need it. And I'm gonna like leave off with some of my own thoughts. So async Rust gets lots of criticisms for being web shit. It introduces syntax like async await, and Rust programmers don't really like that because if you look now, every fifth crate that gets published on crates.io has async functions. And generally, people don't really write async unless they're dealing with the web or I/O, which is kind of like a small subset of things you can do with Rust. So if you have to use an async function from like some library, you have to use something like block on. And people don't like that, but I think they aren't considering the fact that if you look at the biggest adopters of Rust, they're corporations like Meta, Google, Mozilla, Alibaba, Microsoft, and they generally all use Rust for web things. Now we see that Microsoft is slowly putting Rust into the Linux kernel, not Linux kernel, the Windows kernel, and we're starting to see Linux kernel modules getting written in Rust. But the point I'm trying to make is that async Rust has been a huge adopter for Rust, and without async Rust, we would probably all be stuck writing Go and using Go routines, which would be kind of cringe. So yeah, that's it. I apologize for the presentation being kind of messed up, but hey, I think I managed. So yeah, I guess if you have any questions. Yeah.
Little newbie question coming from web, and if I have a CPU bounded routine, something I have to do in my code, but I want to parallelize it. Obviously, I will do it in a thread because I don't want to wait. But I want to make this crate for people to use in their code. My first reflex would be to give also async API for people who just want to do await or want to use it like in a join or like whatever. Would that be, why would that be bad? Because you seem to say that it would be bad.
Well, if the task is entirely CPU bound, the whole reason we have async Rust is to let our code say, okay, I am done with this and I'm waiting for something external. And okay, you can like run something else in the background while I'm waiting for this. So basically, if you can run multiple things in parallel, or let me rephrase, if two things can like, how should I say this? If you're waiting on something external, then that's the only valid reason for async Rust. If you're CPU bound, this becomes irrelevant because you will you will not be able to yield. So you lose the main benefit of async Rust. So the CPU scheduler will then go ahead and say, okay, you ran for long enough, and that will like do something else. It'll context switch you. So it doesn't really matter in that case if you're using async. You're still going to be at the mercy of the CPU scheduler. So in that case, it's way easier to just use system threads or whatever, because yeah, you're not going to be yielding anywhere for your task to store state or like resume later, because it's continuously doing some computation. And yeah, you might like kind of want to do this because like Tokyo exists or all these things, and in that case, like it's kind of easy to like wrap things in like async versions. But like it is a bit of a pain to support. Yeah, yeah. Yeah.
How would you schedule a program which has like half async tasks, maybe interaction with some web services, and half CPU intensive tasks? How would you separate them in code?
Okay, that's a very good question. So I would personally try to only use async for things that require async. And like, so for example, let's say that I'm interacting with some API, and I'm also doing some computation. So for the API interaction, I would like use async, but for the computation, I obviously wouldn't. You might like need to like call the computation thing from the async function, but like it depends on like what you're exactly doing, and it's like yeah. I don't know if like that answers how I would your question, but yeah, kinda, yeah, okay, well, good enough. Yeah.